Our next presenter is Richard Taylor. His presentation is about studying nature's fractal patterns across the arts and the sciences. So let me say a few words about Richard. He's a professor of physics, psychology, and art at the University of Oregon. He finished his Ph.D. at Nottingham University, and he trained as a painter at the Manchester School of Art, United Kingdom. He has a master's degree in art theory, University of New South Wales, Australia. He's the director of the Material Science Institute, which comprises of 35 faculty, over 100 graduate students, and research expenditures exceeding 16 million. He's the director of the Fractal Research LLC and head of the Fractal Research Laboratory at the University of Oregon. Dr. Taylor has worked in the USA, UK, Canada, Japan, Australia, and New Zealand, has published more than 250 papers, and his work has been featured in TV documentaries, has been the subject of popular press articles, magazine articles, and 10 popular science books. He has been honored with teaching awards, such as Outstanding Teacher in Higher Education Award, a Williams Fellowship for Innovative Teaching, the Thomas Herman Distinguished Teaching Award, and a Cottrell Scholarship for Outstanding Teacher Scholars. He has authored and edited undergraduate textbooks, and he has received a number of educational grants. Please help me welcome Richard Taylor.
All right, well, thank you. So I'll talk about studying nature's fractal patterns across the arts and sciences, and I'll obviously talk a lot more about what fractal patterns are. I'm going to begin with one of my favorite pictures, and it's this one. Now, anyone who's a scientist will know that it's a privilege to be a scientist. There's not a moment that I stop and don't enjoy being a scientist. So you might be thinking, well, why have I got this grumpy face? And the reason why is that through the years, many traditional institutes make scientists feel like this polar bear, and they're not complaining about the way the buildings are heated. What it is that many institutes will take a scientist, like a physicist, and they'll put them in this particular department and expect them to stay there. So there's no meaningful way that this scientist can communicate with the other disciplines that are out there on the horizon. And of course, this idea is sort of gradually infiltrated through society. It's even got a name. It's called this the arts-science divide, the idea that you either come from the arts or the sciences, but you can't come from both. And often, where is the blame put for this idea of the divide in culture? And it's often put down to this book from 1959 by a British physicist called Percy Snow, where he declared the two cultures. And it's one of these books that is often cited, but not many people have actually read it. And what people tend to think is that Snow was actually declaring that there are two cultures, that it's natural to have two cultures. He wasn't saying that at all. He was saying that it's unnatural to have two cultures. But with our sort of march towards specialization, if we're not careful, our ability to communicate might stop, and so we might form two cultures. But he was saying it's fundamentally unnatural to have this situation. And many of us know that. So for example, I have a Ph.D. in physics, but I also have a master's degree in art theory. So somehow I've managed to do both of these things. And many of you will be better at more than one thing. So why should society force you to do just one thing? So I got my Ph.D. in physics in the late 1980s, and after that, and I became a scientist. And after that, I started to think about these things a lot more. And in the early 90s, I was traveling in Brazil, and there's a town called Manaus in the Amazon. And in Manaus, two huge rivers come together. And as a tourist, you can catch a boat to the very sort of confluence of those two rivers, and you can look down at all of the patterns happening there. And when I did this, and when I was on that boat, I looked down and I thought, well, the arts and sciences are really like two huge rivers coming together. And, right at the confluence is where all of the interesting stuff happens. So how would you make the arts and sciences come together? And of course, all you need is a common gravity, a common point of interest that both sides want to talk about. And literally on that boat, I looked down at all of these swirling patterns, and I thought, well, it's going to be nature's patterns. Surely everybody, it doesn't matter if you're from the arts and sciences, everyone's got to be interested in nature's patterns. So that's where my sort of career has gravitated towards. And I want to start off with this first picture. Now, this is actually the pattern of an old dried out potato, amazingly. Now, but isn't it amazing how something so mundane can look so visually striking? But there's more. Take a look at this. So this is the old dried out potato. These are actually the nerves in your brain. So this is the electrical circuit that allows you to think. Now, I don't know about you, but do you find it worrying how similar these two things look? No. Because it explains why a lot of us sometimes do feel like we've got an old potato up here, right? But leaving aside those worries, it demonstrates one quite profound thing. And that is that when it comes to patterns, nature has these generic rules that you can take these patterns from vastly different systems and they look quite similar. And the reason why they look similar is because many of nature's patterns are incredibly complex. And so one of the first things I want to talk about is where is that complexity coming from? How is nature building this complexity? So let's start off with a snowflake. And what you'll notice is that snowflake has 6 arms on the outside. But then when you look at the center, this thing's got 6 arms as well. So even in that simple situation, what nature has done is it's actually replicated a smaller version of itself. It's got this big pattern and then a smaller pattern inside. So if you wanted to copy nature, what you could do is you could take a particular, what we call a seed pattern, so in this case a triangle, and then you can keep on adding smaller versions on top of that. And by doing that, you gradually build up this visual complexity. Now, one of the consequences of repeating at different size scales is that if you zoom in on the pattern's going to keep on looking the same. So you can zoom in on this small part, enlarge it, and this thing will look exactly the same as that. And you can keep on going with that idea. And that is that repetition at different size scales is referred to as being a fractal. Now, fractals have been around in mathematics since the 1860s. And the mathematicians felt very good about life. What they were really interested in was this same question. How do you build up this visual complexity? And they loved the fact that they could do it by careful layering. Now, they did look at natural images like coastlines, and they realized that coastlines were complex. But they thought that nature's complexity was just built up by this sort of random, haphazard mess, in sharp contrast to their sort of careful layering that generated complexity. And it wasn't until the 1950s that an incredible British mathematician came along, Fry Richardson, and he was incredibly eclectic. He really wanted to apply mathematics to real-life situations. And this was right at the end of World War II. And one of his things that he became fascinated with was, is there a mathematical theory of why countries go to war? And he came up with this hypothesis that the probability of 2 countries going to war is related to the size of the interface between the two. If 2 countries have a large interface, they're more likely to go to war. So that's why he actually started to look at the coastline of Great Britain, because that's Britain's boundary. And he found this amazing thing out about the British coastline. And then he did something fundamentally unwise. He died, right? which is never a great career move, right? Now, worse than that, he died before he fully promoted his results. So we had to wait until the 1960s when another mathematician came along, a French mathematician called Benoit Mandelbrot, who actually discovered what Richardson had found and then went ahead and actually promoted the work. Because what Richardson had found is that the coastline was also fractal. So nature's patterns are fractal too, but a slightly different form of fractal. So these are the fractals that we were just talking about, the mathematical ones, and they're referred to as exact fractals because as you zoom in, you get exactly the same pattern repeating. Nature works on a far more subtle level than that. Nature's fractals are referred to as statistical fractals because the statistical qualities repeat at different size scales, the general qualities. And one of the consequences of that is when you zoom in on a natural pattern, you don't get a precise, exact repetition. It's just that the patterns look similar at different size scales. But these two families, the exact fractals and the statistical fractals, are equally fractal. And Mandelbrot actually introduced the word fractal as this sort of umbrella term to unite the two sort of fields. And he went on and discovered that many natural patterns are fractal. So, for example, here's an aerial photograph of a river. So you have this main tributary, you have smaller tributaries, and off to the side even smaller and smaller channels going off there. Lightning is fractal, so you'll have a main fork and then smaller versions of that, smaller and smaller versions. Clouds are fractal, so you'll have sort of big bumps, and off to the side you'll have smaller and smaller bumps. So he published all of this work in the early 1980s in a book called The Fractal Geometry of Nature. Now, there are different types of fractals out there in nature. And I want to demonstrate that with these computer simulations. So these, you could imagine that these are simulations of clouds or of coastlines. It really doesn't matter. So each of these four things are fractal. They've got patterns at different size scales. But this one has got way more fine structure in that fractal mix than this one. So they've got similar levels of coarse scale structure, but this has got way more fine patterns going into that fractal mix. And the consequence of having fine patterns is that they look visually complex. So this one looks very sort of rich and intricate. This one looks relatively simple and sparse. So as we go across, what we're doing is increasing the complexity of the pattern. And in fractals, this is quantified by a parameter that I'm going to label as D. And D always lies between 1 and 2. And as you increase the D value, as you move closer to 2, the pattern becomes more visually complex. And this idea is going to crop up in a few times over the course of my talk. So let's give an example of that. Two types of clouds. You can see that this one is very, very smooth. So if I were to analyze that, that would come out with a D value really quite close to 1. This one you can see has got all of this very rich, intricate structure, lots of fine structure. So this D value would be much closer to 2. Now, the reason why we're interested in fractals is mainly as scientists is because different physical processes generate different D values in fractals. So by looking at the D value, you can actually get a sense of what process is going on. So you can imagine in this case, you could almost use this as a sort of novel way of weather forecasting. You could actually determine the D value of the cloud, and that will give you an idea of, for example, the wind patterns that are going on up there in the sky. Let me give you another example. So I lived in Christchurch in New Zealand for 2 years, and Christchurch is right on the edge of what's called the Banks Peninsula. So let's have a look at these coastlines. So on the Banks Peninsula, the process that generated that is volcanic, and that leads to a very jagged coastline, quite complex. I'd say probably around about a D value of 1.7. If you move further north, this is generated by a very different process. It's generated by just gradual erosion by the waves. And you can see that that's much sparser and more simple. So there's another example of different processes generating different D values. Now, of course, with coastlines, they're fairly static. They don't really evolve much with time. But you could study examples where coastlines do evolve with time. For example, in the Antarctic, a lot of the coastline there is actually established not by landmass, but by these huge ice fields. And they can shape some of the coastline. In particular, there's this big ice shelf here called the Larsen B ice shelf, and that's where a lot of the scientific research goes on. One of the good things that the US military does is it actually flies all the scientific apparatus that there is down to the Antarctic. So without the US military, there would be no research going on in the Antarctic. But they ship a lot of their stuff off to the Larsen B ice shelf, where various scientists do their work. This satellite photographs of the Larsen B ice shelf. So this is 1986, and this is more recently. This huge collapse that's gone on is thousands of square kilometers. And what research programs like Gateway Antarctica do is they send their scientists onto the Larsen B ice shelf. So you can imagine that these scientists want to know when the ice shelf is about to collapse, right? So that would be useful information. So what we're doing, we're working with Gateway Antarctica. You can see that as the ice shelf collapses, the fractal patterns actually change. This D value is around about 1.5. This is much closer to 1. So in that project, what we're using is satellites are going over the Antarctic quite frequently. So we analyze those pictures. We determine the D value of the coastline, and we're hoping that from the change in the D value, we'll be able to predict when the ice shelf is about to collapse. So using fractals is useful. It's probing physical processes. The other thing that these pictures kind of emphasize is that as technology increases, our ability to look at fractals gets better and better. So I just mentioned that this comes from our ability to take satellite photographs. We wouldn't have been able to do that 100 years ago. And just as technology is increasing to looking at fractals out there in nature, technology is also increasing to look at fractals within our body. So for example, apparatus like MRI units are allowing us to probe into the human body in a non-invasive way. And so, for example, one of the projects that I'm working on is looking at the neurons in the brain, these sort of electrical circuits, and actually analyzing the fractal characteristics of the brain. Now, the reason why fractals are so prevalent in nature is not because nature likes the look of these patterns, it's because of the interesting functional properties that they get out of being a fractal. And so a lot of my research is based on this idea of biomimicry, that we take a look at nature, we learn what it's being up to, and then we apply that to an artificial system. So let me take a few moments to tell you why nature actually uses fractal patterns. So let's look at the neurons in the brain. One of the great properties of all of this repeating structure is the connectivity that you get out. All of that complexity of those branches allow neighboring neurons to come together and connect and form the circuit. And that, of course, that circuit is what allows you to think. So connectivity is a major favorable functionality that you get out whenever you have fractals. Let's look at the lungs. Your bronchial tree is fractal. It's got all of these branch patterns. One of the amazing things about fractals is all of these repeating structures build up an enormous surface area. Look at this. So the surface area of your lungs is about the area of a tennis court, and that area is all crammed into a volume of a few tennis balls. It's an amazing mathematical shape that all of that repetition generates an enormous surface area within a small volume. And so it produces a huge interface. And that's exactly what your lungs need. It needs a huge interface for allowing oxygen transfer. The same thing happens for trees. All of that repeating structure generates an enormous surface area for collection of solar energy. Another thing, got back to the coastlines, all of those repeating structures disperse wave energy. So although coastlines erode a little bit, they don't really erode a lot. They don't change much. And it's because of all of this fractal structure actually disperses all the wave energy coming in. So for example, in harbors now, storm barriers used to be these flat surfaces. Now in harbors, they're actually building storm barriers that have got fractal shapes to disperse the energy. So those are physical structures in nature. A lot of motions in nature, if you look at the pattern traced out by the motions, that's also fractal. So let's look at this albatross. The albatross flies around the Antarctic skies and it forages for food. So let's look at the various strategies that an albatross could use to actually find the food. So let's consider it could fly along a one-dimensional line. That will get it from point A to point B very quickly, but it could miss out on all of these food sources off to the side. This is a random trajectory. This is assuming that the albatross doesn't have any particular strategy. It just does a haphazard motion. Random motion actually does concentrate in one area. So if the food was here, the albatross would find it. But the trajectory doesn't diffuse very quickly. So if the food lies over here, the albatross is really not going to find it. Now let's imagine that the albatross actually flies along a fractal trajectory. So then what happens is that the albatross will do a few small flights in one area where it's foraging. Then it will do a longer flight. It will forage in that area. Then do an even longer flight and gradually build up this fractal pattern. It turns out that mathematically, this fractal trajectory is an incredibly efficient way to cover space. And if you're searching for something, that's exactly what you want to do. You want to cover all space, so you'll find this. So some researchers have been looking at the flights of the albatross, and this is what one of them looked like, and that they're declaring that the albatross somehow knows this through evolution, that it's a good thing to adopt this fractal trajectory. And it's a little bit controversial at the moment, just because of the measurement techniques. They can't quite determine whether the albatross is fractal or not. But lots of people are studying this. For example, not just albatrosses, but lots of animals, from sharks through to bees, whether their patterns of motion are fractal. The amazing thing is that other researchers are also studying human beings, that are actually looking at the way that people forage in their daily lives. This is one individual, and the white is a whole set of other individuals. And the way that they're monitoring you is using your cell phones. And so, again, the jury is out as to whether you're actually using fractal trajectories in your everyday life. But if you want to cover space efficiently, a fractal trajectory is the best way to go. So getting back to this idea of the book and the two cultures, and what C.P. Snow said. He said, well, the thing that might create the divide is our sort of march towards civilization, if we haven't got any communication. And so early on in my career, I started to think, well, maybe nature's fractal patterns are the way that the arts and sciences can communicate. So what I want to do is sort of take you on sort of two journeys. One journey of what I've been using fractals in with the sciences, and then let's come back to the arts later on. So what I've been studying in my sort of main projects in science is fractal electricity. And sort of my hero is this guy, Tesla. And you can see here in his laboratory in Colorado, he's got all of these amazing bolts of fractal electricity happening. So he was sort of like the pioneer of fractal electricity. But probably most of us wouldn't be this calm, right, with this going on. That it's not a fundamentally safe way to go. So a better way of generating fractal electricity is to actually build a circuit that is fractal in shape. So when you pump the electricity through it, then the electricity will have a fractal shape. So this is called a nanoflower. It's made out of a metal, and it's about a micron in size. So a micron being 1,000,000 times smaller than a meter. So when we pump current through this thing, a fractal current will actually ensue. Now you might think, well, that's kind of nice. I've built fractal circuits, but what's the use in that? Well, what we're doing is that, and in fact, a number of commercial companies have emerged over the last 10 years. And what we're doing is developing electronic chips to put in the back of the human eye. And the reason for that is that millions of people each year get diagnosed with diseases of the retina. And in your retina, you have these photoreceptors. Those are the things that receive the light and convert it into electricity. And when people get these diseases, it starts to wipe out the photoreceptors, and they start this sort of long journey towards going blind. So what we're doing is developing these chips, and on these chips they have the artificial photoreceptors, what are called photodiodes. They do exactly the same thing. They receive the light and convert it into electricity. People are always surprised to find that this is already going on. So the surgeon can place this chip in the back of the eye, so the light will come in, it will generate electricity, then that signal has to pass through the natural nerves and then down the optic nerve to the brain, and you see. So where we're at is that these chips work, but they don't work very well. And the problem comes at this interface. How do you interface the chip with the nerves? And I think, no, you won't be surprised to find that the nerves in your retina are fractal. They've actually got these branch patterns that repeat. So that's what we're doing. We're growing on the surface of the chip these artificial neurons so that these will charge up and they will communicate the signal to your nerves in your brain and pass on the signal. We're doing this not just to put into the human eye, but of course in the future we're going to have these little guys running around looking after us, these little robots, and they're going to need eyes too. So we're developing this also for artificial vision. Some of you might have seen this a couple of years ago. So the year 2045 is a sort of mysterious year where we're going to build computers that have the same number of components as the brain, and that's when people think that maybe the computers are going to get consciousness and all of that craziness. Now, you can regard this as science fiction, and it is science fiction. But the idea of actually building circuits and putting them in the brain is not science fiction. Today, about 80,000 Americans are walking around with electrodes in their brain to treat conditions such as Parkinson's disease. So the electrodes are already in people's brains. So we're just developing better electrodes based on them being fractal because the neurons in the brain are fractal. Now, these chips have photodiodes in them. They receive light, convert it into electricity. So you're probably starting to realize, well, there's an awful lot of similarity with solar technology. Now, have you ever stopped to wonder why solar panels look this way? Because nature's solar panels don't look this way. Nature's solar panels are built on a fractal geometry. So half of our grants are actually on developing new solar panels. And this silver thing on top, this is what's called the top electrode. That's the thing that sucks the electricity out of the solar device. And that's the design that is on everyone's rooftop at the moment. What we're doing is, from biomimicry, is replacing that with a fractal design. And we're finding a 14% increase in efficiency of the solar cells, which relatively is a huge amount. So hopefully from that journey, you'll get a sense that scientists are actually doing pretty good in terms of biomimicry. They're looking at nature and applying it to technology. So what I want to do is ask the same thing about art. Can artists do the same thing? Because I'm sure a lot of you have started to look, and not just in my talk, but previously you looked at these fractal patterns and thought, wow, these are really quite visually stunning things. So how would an artist go about generating a fractal pattern? Well, let's assume that they're going to do the same thing as the scientist. They're actually going to try and harness some process that generates it for them. What process would they actually go looking for? So many natural processes work on something called chaos. And what chaos is an extreme sensitivity to the environment. And in the 1960s, as an example, the weather patterns were found to be chaotic. So even the smallest change in the environment, for example, whether a butterfly flaps its wings or not, can change the way the weather condition evolves, to the point it can change whether a tornado is induced in the future or not. So that's chaos. Now you might say, well, how could an artist harness chaos? They can't kind of control the weather, right? No better than anybody else. How can you harness chaos? Well, there's a much simpler way to harness chaos, and it's related to a game of billiards. This is one of my students, Ian Pilgrim. In the 1970s, a Russian chaos theorist called Sinai started to study the mathematics of how you play a game of billiards. So this is our standard game of billiards. And this is not chaotic. This is very, very stable and predictable. Otherwise, we wouldn't be able to play the game. So if you launch a ball, it might follow this blue trajectory. Change the conditions just slightly, move the ball a little bit, now relaunch it. And it does more or less the same thing. So it's very, very stable. What Sinai found is the game completely changes when you introduce a circle at the center. That induces chaos. You launch the ball, it goes along the red trajectory, ends up here. Just change things just a little bit, and it evolves in a completely different way. Now, what scientists have learned over the years is when you get this chaotic dynamics, it generates fractal patterns. Now, that's quite hard to see if you're looking at a ball rolling around a table. So let's do this where we replace the balls with rays of light, because then we can photograph it and see the fractal patterns emerge. So let's build the equivalent thing using light. So what we've got is a cube of mirrors. And in the middle of that cube of mirrors, we're going to put a big spherical mirror. And we're going to shine rays of light into this box, and they're going to bounce around. So this is looking on the inside. So this is using dry ice, so you can see the lasers. So if you haven't got this circular scattering, you get this very stable behavior. As soon as you put the circular scatter in, it generates the chaos. So if we go back to the apparatus, I've obviously taken the top mirror off so that you can look inside. But for the experiment, you'd put the top roof on top, and then you've got 4 holes in the corner, and you could shine a blue light in, a red light in, and a green light in from here, and then you take a photograph in at the 4th hole. And these are the patterns that you get out. So you generate all of these amazing fractal patterns, and you essentially get them for free. You've just combined 2 simple patterns, a cube and a sphere. You sit back, and the chaos will generate the fractals for you. This is actually a permanent exhibit that we generated for OMSI in Portland, which is the Oregon Museum of Science and Industry. You can see its size. It's about this size. But what we're planning to do is build a massive version where someone could actually walk through this thing and completely surround themselves with fractals. So I think that this is the way that artists will go if they can harness somehow some natural process to generate the fractals for free. And this idea fascinated me right at the start of my scientific career. In the early 90s, just as my sort of scientific career was taking off, I really got interested in this idea of whether artists could actually generate fractals. And I actually got a fellowship and took a year off and went to art school in the early 90s and in England. And this is actually a sketch from my sketch pad on my very first day at art school. And you can see I was being very optimistic at the time with this bright idea. And I thought, how would an artist generate fractal patterns? So I thought, probably one of the easiest way would be to use a pendulum structure, because then you could have a container, fill it with paint, have a hole in the bottom, that would drip paint, put a horizontal canvas on the floor. And then here comes the tricky bit. How do you introduce the fractals into the motion? So I thought, well, maybe the artist could grab it and they could put some small shakes in there and then some bigger ones and some even bigger ones. And that would build up a fractal motion. And you would get a fractal pattern appearing on the canvas. So I always feel sorry for my parents because, of course, parents think they've got rid of their kids, but they never did. And so when I went to art school, I went back and lived with my parents and converted their garage into my studio. But all that it did was generate this colossal mess for them in the garage. And I just couldn't do it. I tried to introduce all of this motion, and I would never get a fractal pattern out. So I was just on the verge of giving up. And like a lot of times in life, just when you're about to give up, something in life, if you keep your eyes open, will come along and help you out. And with this example, what it was that as part of the course, what they made the students do is they sent us all up to the Yorkshire Moors, which is a sort of very bleak part of the top of England. And this is the Yorkshire Moors on a beautiful day, a typical day, you know, it's all storms and snow and whatever. And what we were told to do is that they took us up to the Yorkshire Moors and they said, you've got a couple of days to somehow capture nature that you see. And we arrived there in this snowstorm with all of this stuff going on. So we realized that, you know, the idea of using sort of traditional paints and pens and whatever was completely out because these gusts of wind were completely wild. So we do what all great art students do in times of crisis. We went down the bar and had a beer. And while we were drinking, I was telling my friends about this great story about a French abstract artist called Yves Klein. And what Yves Klein did once, he was in Paris, and he had to drive down to Toulouse in the south of France to actually give a gallery down there a painting. And what he did, he took an empty canvas, put it on the roof of his car, and as he drove down south, he actually passed through this huge thunderstorm, and all of the wind and rain created this pattern on the canvas. So when he got to Toulouse, he walked into the gallery and said, here's the painting, nature painted it, now you give me the $10,000. And he got the $10,000. So I was sat in the bar thinking, well, this is a great idea. We've got all of these gusts of wind and rain. Why don't we get nature to paint for us? So you're going to be seeing lots of my holiday snaps, by the way. So this is me in the early 90s. The storms had been so vicious that they'd actually knocked down a whole set of trees. So we built this massive pendulum structure out of all of the branches. Now, from my scientific career, I'd read papers which proved that when a storm comes along, all of the wind trajectories are fractal. You've got these big gusts of wind intermixed with smaller gusts, intermixed with even smaller gusts. So what we did is we put a big sail structure on here. Then the fractal wind trajectories knocked this around. That transferred that fractal motion to this part. And on that part, we had paints, and below that, we had a horizontal canvas. And this is what the fractal wind actually generated. So I thought that that was sufficiently interested to pursue this. So after my year at art school doing the painting, I actually moved to Australia to resume my scientific career. And the weather's slightly different in Sydney, not so many storms. So what we built is this apparatus that has since become known as the Pollockizer. And instead of the wind patterns knocking the thing, you can actually program a computer to deliver some fractal knocks to it. And this is the sort of thing that you can get out. So this is sort of like the regular pendulum before you do any knocking of the string. So this is just very regular. This is when you get the fractals out. And then for comparison, this is a section of a painting by the artist called Jackson Pollock. So his paintings look sufficiently close to the fractals that we started to ask, well, did Pollock then somehow harness some natural process to generate his fractal patterns? So who is Jackson Pollock? So he's a famous American artist from the 1940s, early 1950s, where he developed this radical technique. He would roll these huge canvases along the floor, and then he would simply pour paint onto these canvases, generating these very complicated patterns. Very sort of revolutionary at the time. His paintings are now worth more than any other artist, valued anywhere up to $600 million each. Really quite remarkable. So through the years, I then went on and did an art theory degree on Jackson Pollock. And through the years, all of the art theorists have declared that Pollock's paintings were natural looking. And they used to refer to them as organic and using words like that. but they didn't quite know what organic meant. So was it that, when they said it was natural looking, was it that his paintings were actually fractal? And certainly when you compare his paintings to, for example, nature's fractal patterns, so for example, branches in the trees, they look very similar. These are actually neurons in the brain. So these are fractal neurons. But again, compositionally wise, they look very similar to a Pollock painting. So in the late 1990s, what we did is we took all of these computer pattern analysis techniques that we were applying to our scientific work, and we applied them to Pollock's work, and found that the sort of graphs that they came out with were exactly the same as the graphs where if you pass this through for a natural pattern. These things were just as fractal as natural patterns and computer-generated fractals. And actually now, since then, about 10 different groups have used different types of pattern analysis to investigate Pollock's works. He's one of the most researched artists from a scientific point of view. The thing that we were really interested in, though, was the process. How did Pollock actually harness some sort of natural process to generate the fractals? Now, to pour paint, you have to lean over. But what everyone knew is that Pollock leans way more over than he needed to. He actually deliberately went off balance when he painted. So we thought, well, maybe it's something to do with the physiology of human balance. So what we've been doing, you can use motion detection laboratories where these markers give off infrared, and then you can have an infrared camera. So you can actually monitor the motions of someone while they're painting. So we could look at the fractal patterns evolving on the painting, and then look at the fractal patterns of the motion where they're coming from. What's really interesting is we got 40 adults to actually paint in the style of Jackson Pollock. And then we went one step further. We got a similar number of little kids to do the same thing. Now, at first, we thought that this was going to be just a little bit of fun. And certainly it is a lot of fun. I often get called out to do these sort of be a judge for who produces the best painting. But what was amazing, it became very clear early on that the paintings that the kids were producing were much closer to Pollock paintings than what the adults were doing. Let me remind you about this sort of visual complexity, D value of 1 to 2. If it's got a higher D value, it means it's got way more fine structure in than a low D pattern. This is what we found. So this is the D value of the painting. So this is what the adults were painting, very high D values. And this is what the kids were painting, lower D values. Now this is the D value of the painting, but presumably that D value came from their motions. So the kids had a very different motion than the adults. Both were fractal, but the adults had high D values. Now what's the difference between kids and adults? Well, there's lots of difference, but there's one striking physiological difference. At the age of 5, their physiology of balance has not yet matured. Kids are still not very well balanced. So it seems to indicate then, if you are well balanced, you have a high D value. If you haven't quite got a good balance, you have a much lower D value. So the million-dollar question is, where did Pollock sit in all of this? And he sits here. So he's within the adult distribution, but he's towards the kids' end of town, indicating that he must have had poor balance. And what's interesting from an art historical point of view, you read all of the popular books about Pollock, and they say how graceful he was, and he was almost like a ballet dancer. Talk to people who actually knew him, and he was actually notoriously clumsy. And he actually had a medical condition that gave him poor balance. So what we think is going on is that when you go off balance and you have all of those swaying motions, and how do you restore balance? We think that your body assumes a fractal trajectory. And if you think back to the Albatross, that kind of makes sense, because what your body is doing is it's got a certain amount of space, and it's searching through that space for the ideal balance condition. So what trajectory does it pick? It actually picks a fractal trajectory. Now, I think that this is a great example of how you can defeat this sort of art-science divide, because on the one hand, this research is telling you something about the great art of this painter, but on the other hand, it's telling you something about the science of human balance. And our colleagues are investigating this to actually learn more to do with whether therapy is working after an accident. You can chart the D value to see if the therapy is actually working. Is the person actually restoring their balance or not? The other thing I want to emphasize is that Pollock wasn't a victim of his physiology. He actually deliberately exploited it. He leant over way more to trigger this particular condition. Now, why did he do that? Well, I don't think it's any coincidence that he started to pour paint when he moved from downtown New York, which doesn't have any fractals in its scenery, to the countryside, where it had lots of fractals in its scenery. So perhaps Pollock was actually responding to the fractal in his environment. Now, if that's true, Pollock can't be the only person who does that. He can't be that unique. So there must have been lots of people before him who actually could also, in some way, sense the fractals out there in nature. So how easy is it then to actually look there out on nature at nature's fractals and then actually paint them? And I started this question, not when I was at art school, but again, when I was traveling. I was traveling through Tibet, and there was an accident on the road. And the consequence is that I had to spend 3 weeks in this Tibetan monastery, and this is no joke. Now, what happens with 3 weeks in a monastery? You think that the monks are going to tell you some great meaning of life, don't you, hopefully? So what happened is that all that they wanted to do was arm wrestle every morning. And every morning they would beat me. But the amazing thing is that one day I was doing the arm wrestling and I was getting beaten by them, and I looked down at the tapestry and I noticed all of these repeating patterns. So the Buddhist monks had actually got there before Pollock. And so when I managed to get out of Tibet, I went to the libraries and started to look at all of the different research of different cultures. And it turns out that lots of different cultures across the world from different centuries have all got clues of these fractal patterns in their artworks. And I just want to take you through a few sort of famous examples. So this is the Great Wave, a woodcut from a Japanese artist called Hokusai from 1846. And you can see on top of the Great Wave, he's got these smaller versions of a wave. So he has replicated the pattern. And this wasn't a coincidence. You look at his artworks, for example, this is called The Ghost. And he did a whole series of these. Now, fissures in your skull are actually fractal. And if you zoom in on this fissure, he actually got several layers of different bumps in there. Okay, so you've got to give Hokusai sort of credit for spotting the replication of patterns in nature, but he didn't quite get there. This is what the Great Wave would look like if you actually used mathematics to generate the Great Wave. So this kind of gives us a clue that if you're going to go this route in terms of generating fractals, you're going to have to use mathematics to do it. So who are the great artists who knew about art and knew about science? And obviously Leonardo da Vinci comes to mind straight away. So Leonardo had lots of adventures, but one of his great things was he wanted to build a flying machine. And more recently, they've actually assembled flying machines, looking at his notes, built them, and found that they did fly. He knew that to actually build a successful flying machine, he would have to study all of the turbulence in air currents. But he also knew, of course, that you can't see air turbulence. So that's why when you look in his notes, he's got all of these studies of turbulence in water, where he inserts these various objects into the water. And he studies the appearance of the vortices, the sort of swirling water. So this is a sketch from 1500 called the Deluge, and you can see these big swirls of water and smaller swirls still. So this is a great example. You could consider this art or you could consider it science, and it's actually both. even though he's captured these swirling patterns on multiple scales, if you were to scan that into a computer, it's not actually rigorously fractal. He hasn't quite got there. You really would need to use mathematics. So who could do that? So a famous graphic designer, a Dutch graphic designer called Mork Escher, is famous for actually looking at mathematical principles and generating his art that way. So in the late 50s, early 60s, he generated all of these tessellation patterns. They're really quite amazing things. They're based on mathematics. He actually went and read papers by a British mathematician called Donald Coxeter, took those patterns, generated the framework for his paintings, and then he started to input all of the sort of artistic tessellations on top of that. But it's absolutely amazing. You look at all of what are called the aesthetic flow lines in these patterns to actually capture this thing. So I'd say if there's ever an artwork that you want to point at that says uses both art and science, then it's one of these things. And I'm working with an artist at the moment, Ben van Dusen, that actually kind of works beyond all of Escher's work. So what was going through Escher's mind when he was carefully doing these things? When you read a lot of articles about Escher, they say that he was very much into the pure mathematics of things, but it's actually not true. At the same time that he was generating these tessellations, he was doing many, many sketches of natural patterns, of vegetation. Take a look at this one. This is a drop of rain on top of some leaves. And the leaves are actually, the veins in the leaves are actually fractal. And what the water drop has done is magnified those things. So Escher really did know about fractals, even though he was doing this in the 60s, and Mandelbrot didn't come along until the 70s. So there's these sort of two ways that artists can think about generating fractal patterns. Jackson Pollock harnessed the natural process and kind of got the fractals for free. That we actually labeled as fractal expressionism. Or you could follow sort of Escher, where you actually have to do something substantially harder. You have to really observe nature and then come up with some mathematical strategy to generate what you've just seen. In terms of this mathematical route, then we have to give Benoit Mandelbrot the credit, because having in the 70s noticed all of these fractal patterns in nature, what he did in the 80s was use computers to actually generate the fractals. This is the very first mathematically generated fractal from March 1980. It's named after Mandelbrot by other people. It's called the Mandelbrot set. And this is what you get in 1980 using the he was at IBM, and he used the full might of the IBM mainframe computer, and this is all that it could do in 1980. This is what any of your laptops can do today. So we really are of the era of fractals, and it's often been said that computers are to fractals what telescopes are to astronomy and what microscopes are to biology. Now, some people shy away from this. They say, oh, well, this really isn't artistic. You're using computers to generate these things. So I want to show you one more example. Imagine doing this following thing. You use the mathematics to generate the pattern, and then you do this. So this is absolutely incredible. These are crop circles. They've been popping up in England since the 1600s. And then in the 1980s and 90s, there was suddenly a huge explosion of these artists doing these things, and it spread around the world. Look at this. This is called a triple Julia set. This was done in one summer's night in 1996. The rule that the artists have is that they have to do it in one night, and they can't be seen doing it. Now, these things now, the things that are coming out now, can be up to 1,000 feet long and have 200 components to them. They have one more rule that makes things really, really difficult. They're not allowed to break a single stalk in the pattern. You go into a crop circle, and they're all carefully textured. Not a single stalk is broken. Now, if you think that that's really strange, I should pause and say, how many people actually think it's aliens? Excellent. It's not aliens. Biophysicists have started to get interested in this phenomenon. In your crop stalk, you have knuckles, things that are called pulvini. These are the samples that they take from the actual crop that's in the pattern. And the stalks have been enlarged. These are controls taken from the same field away from the crop circle. Here's a plot of the size of the knuckle against the position in the circle. The red ones are the controls from outside, so they're small. The ones inside are expanded, and they get bigger towards the center. So this is all speculation, but a couple of years ago I published an article, and you might say, well, what weird journal would publish that? It was actually Nature, which is one of the most prestigious scientific journals. One possibility that could explain this is that the artists are actually using microwave radiation. And just like in your microwave oven, what it does is it superheats the stalks. All of the water turns to steam that enlarges the stalk. It becomes weak, it falls over, and then it cools in the horizontal position. So if these artists aren't doing that, they should really think about doing that, you know. So where we're at then is we live in a world where there are fractals out there in nature. Science is really using fractals. Artists are using fractals. So the big question is, well, do we actually like them? And so what we've formed over the last 10 years, it's called a center, but it's more a virtual center. It's a sort of international network of different scientists actually studying the aesthetic response of fractal patterns. I just want to show you a few results. So when you look at an artwork, what does your eye do? What sort of pattern does your eye trace out? You can use eye tracking facilities. You can flash up the image that you're interested in on a computer monitor. You can use an infrared camera to look at where your eye has been going. If you flash up a complex pattern and your eye goes into search mode, so it's actually looking for something in that complex pattern, you're probably not surprised to find that what our research shows is it actually traces out a fractal pattern. Irrespective of the thing it's looking at, if it goes into search mode where it's got to hunt for visual information, it automatically, intrinsically goes into a fractal motion. And I think you can tell me why. It's because a fractal trajectory is the most efficient way of covering space, which is what you want to do. The albatross is looking for food, but your eye is searching for visual information, but it needs the same strategy. The interesting thing is that everybody has a D value of 1.5, irrespective of what you're looking at. So this is the interesting question. If your eye has this intrinsic motion, a fractal motion of a D value of 1.5, what happens if you show a person a fractal pattern of 1.5? Is there some sort of resonance that you get due to the commensurability of the fact that your motions are exactly the same as the structure you're looking at? Now, resonance is a very woolly word, so we can get more technical than that. What will happen is that your eye will find it very, very easy to process the visual information that it's looking at. And there's a whole theory of aesthetics which says that if you find something very easy to visually process, you will actually like looking at that thing. It will have aesthetic value. So we started on all of these projects and we published them. Lots of other groups have got involved. Over 1,000 people have now been studied. And people really like these fractal patterns of a D value of 1.5. It goes even further than that, though. When someone looks at a D value of 1.5, it changes your whole physiology. You actually relax considerably. One way of measuring relaxation is skin conductance. That's a very traditional measure that's used in lie detectors, for example. When you lie, you get stressed, they measure your skin conductance. So we found, using skin conductance, that when you look at these magic fractals of 1.5, you relax by over 60%. You can see where this gets fun, right? So EEG, where you put electrodes on somebody and you measure the brain activity, there's a particular brain activity called alpha waves. You actually have these waves passing through your brain at about 13 hertz. And it's well known that when you are relaxed, your alpha waves peak. When we show people these fractal values of 1.5, the alpha waves increase substantially. We're now using MRI. It turns out this is your primary visual area where all of your information gets dumped initially. Then you have these higher visual areas. It turns out that these magic fractals activate completely different regions of the brain than other patterns. So in some sense, you really are hardwired to appreciate these patterns. So all of this research was funded, well, some of the research was funded by NASA because they wanted to keep the stress levels of astronauts low. But what about the rest of us? We all need to be de-stressed. Now, to give you the idea of what we're up against, America spends $300 billion a year on stress-related illnesses, and that's typical. The UK also spends the same amount. About $1,000 per person is wasted on solving stress reduction. So what we want to do is work with artists and architects to see if we can actually incorporate these fractal patterns in everyday life. Now, I've made a start with this. I waited until my wife had gone out, and then I painted the refrigerator. And it turned out to be a failed experiment. When she came in and found what I'd done, her stress levels went up, not down. But she has since forgiven me, and she has since come to like the refrigerator. So we could work with artists to actually paint these fractals, but we could go one step further. Nobody thinks that architecture based on blocks is a particularly good idea. It's been speculated for a long time. Can we actually start thinking about fractal architecture? The big stumbling block there is, okay, they may look nice, but how much money is it going to cost to build these things? And what's happening over the last 5 years is an amazing revolution. I think this university will have them, 3D printers. You can program things into a computer, mathematically precise, and then the printer will produce these things. So I'm working with a sculptor actually in Australia, Danny Delabosca. These are the things that he's generated. But 3D printers are getting bigger and bigger. They're so big now you can print a whole room, and people are starting to talk about assembling buildings. So we really might be of the era of fractal architecture. The interesting thing is that fractals have been going on all of this time. It's just that now they're easier. Gothic architecture has repeating patterns. The outlines of African villages have fractal characteristics. So people have been doing this already. It's just that now we're a lot closer to doing it really quite easily. Even in Beijing at the Olympics, the Aqua Center was built on these bubbles, and bubbles have got fractal distribution to them. In all of this, as an artist or as a scientist, you might as well make life easy for yourself. So you could do this. You could start off with a Euclidean shape and introduce your fractals using nature. Or you could even do this. I'm working with one artist on what are called perceptual fractals. Instead of building the fractals, why don't you get nature to actually assemble them in your mind? So what this artist is doing is putting all of these little triangular shapes together so that when you look at them at a particular angle, this is a bit washed out, you get the fractal. Let me show you another picture. So again, the objects themselves are not fractal, but when you look at them from a particular angle, your mind assembles the fractals for you. So what is it like to be a scientist? It's actually a lot of fun. Have I got a couple of more minutes, Costas? I want to tell you one more thing that I've started to notice relating back to the idea of two cultures. And it's this question. We've been talking about art and science as being fractal. It seems to be that nature works on fractals. What I've been starting to think about, does creativity itself follow a fractal pattern? So let's just review the journey that we've been on. I started off with these scientific structures, electrical fractals. I was building those because I wanted to build an electronic circuit to go into the brain. Along the way, though, I noticed the amazing aesthetic quality of the fractals. That made me ask the question, have any artists been generating these fractals? And I found out yes. Then I started heading off on, okay, these artists have generated these fractals, so, what is the aesthetic quality of these things? And so in my career then, I was meant to be going this way. I was meant to be, I was funded to do all of these chips in the eye, but I was heading off also at the same time on this other trajectory. And at some point, I started to get worried. Maybe everything's spreading out and getting too diverse. But then what amazing thing happened is that these diverse projects actually folded back in and helped the original project. It turns out that all of that research on stress reduction we need to know for the original design. If we get the chip wrong, we will put it in the person's eye, but it won't trigger the original stress reduction mechanism. So could it be that the natural process of creativity is actually fractal? If you plot it as a function of time, these trajectories are you exploring your interests in interdisciplinary space. So you actually start to spread out and you might follow particular trajectories. If you go with that fractal pattern, perhaps that looks after you. So just when you think it's spreading out and getting too diverse, maybe it folds back in again based on your natural interests of life. So a couple of years ago, I held a public event where we got Freeman Dyson in, who's another famous scientist, and we kind of chatted. It was the oddest thing. It was a bit like today's thing, actually. We kind of chatted, and there were 300 people looking at us. But he has this idea that there are two types of people in the world, the hedgehogs and the foxes. And the hedgehogs have very narrow interest in life. They know where they're going and they head off in that direction. So you have these whole sets of hedgehogs. Then you have the foxes that actually go between the hedgehogs and actually cross-pollinate. And what's interesting about this, it's sort of an unfortunate name because no one wants to say, I'm a hedgehog. But Dyson did point out it's actually the hedgehogs, the people with the real focus, who go on and get the Nobel Prizes. But the foxes are needed also to bring in a new perspective. I don't think it's that discrete that you've got hedgehogs and foxes. I think there's a range. Some people will have a narrow range of this tree. Others' comfort zones will spread out a lot more. But if this is true, and this is just speculation, this is an incredibly important thing to do for a university, is that if this is a natural process, you've somehow got to jump into that river and go with that natural process. The worst thing that you can do is step in and start trimming these things down. So from a university point of view, you have to create the environment for whether it's undergraduates or graduates to allow them to go along this natural process. And the worst thing you can do is bump into somebody who declares that you must be one thing or the other, because you don't. That will be knocking out all of these potential trees, which will be good for you to actually explore. All right, so I will end up with that. What is it like to be a scientist? It's really great, but it's particularly fun as a scientist if you can work with artists as well. So thank you for coming on that journey with me.
Richard, not more than a couple. He'll be back at 1 o'clock downstairs at the Key West room, and he'll have the chance to answer individual questions a lot more extensively. So, if anyone wants to ask any questions.
Yeah.
Could there be fractals in music?
Yeah, so some people, we've concentrated on mainly the visual fractals, but a whole set of physicists have looked at lots of different fractals based on the inspiration that lots of natural sounds like waterfalls and even bird song has been found to be fractal. So people have looked at different types from classical music to more modern music and looked at the fractal characteristics. One of the projects that we're doing is taking some of Pollock's paintings and taking that visual information and converting it into music. so that you can have some sort of event where you go in front of the actual painting and you hear what it sounds like as well. Yeah?
At the beginning of your talk, you said that D value that you were using has limits of between 1 and 2.
Yep.
Where does that come from, and what occurs at those limits?
So I can take you and show you all of the analysis, but for the moment, it is actually a dimension. That if you look at some of these fractal patterns like a branch tree, the individual branches are one-dimensional lines, but they spread across and fill a two-dimensional space. So they actually have this really exotic quality where they have an intermediate dimension that lies between 1 and 2. So it really is a dimension in some sort of sense. Yeah?
What you said before about the dimensions, are fractals higher dimensional concepts basically portrayed on a lower dimensional plane?
Yeah, it's kind of two things. One is the thing that makes up the pattern, that's referred to as a topological dimension. And then the thing that it fills is called the embedding dimension. And we're looking at profiles of things that actually land on your eye. But the physical things like a mountain, its D value actually lies between 2 and 3 because it's actually spreading out into three-dimensional space. And it's just that the image falls onto our retina, which is embedded in a two-dimensional space. Yeah?
You mentioned the mantras, like the Buddhist mantras. Is it that they're being spoken in a fractal pattern? That they give them like a sort of spiritual quality?
It could be. I mean, when one of the things that we sort of started off this project with is that, this sort of language that when people looked at a Pollock painting, they said, well, I feel this sort of resonance, and never said anything beyond that. And that was our sort of clue. Whenever you hear the word resonance, it's some sort of clue that for whatever reason, for evolutionary reasons, we're naturally aligned with these structures. And so it could be the same with sound and mantras and things like that, that there's something going on, this unique thing of evolution, where we're at one. I know that sounds sort of very new agey and whatever, and I think that's one of the things that we've done. We've taken those sort of new age sort of feelings about fractals and actually brought some sort of scientific quantification to the process. Yeah?
I have another question. Do you think the best way to actually generate fractals in art is through 2D representation or 3D?
Well, what we're doing is there's a psychological condition referred to as synesthesia. And a lot of artists experience this, and it's translation across the senses. So some artists can hear music and they see colors. And what we're trying to see is is there any sort of similarity between different senses. So music may be one thing. We're finding that with visual fractals, people really like a complexity of D of 1.5. Is that the same with music? And one of the big things is touch as well. So what we want to do is these sculptures that I showed you are going to be part of psychology experiments where we're going to get people blindfolded to actually touch these fractals of different D values and see if there's a preference. But there's no doubt the more that you become part of the environment, the better you are. I think 3D fractals are going to be far more important than just 2D fractals. And time-evolving fractals as well in particular. Yeah?
I was going to ask, is different pictures of nature, do they also follow the 1.5 fractal thing between different forest types?
Yeah, it's a great question. So no one's done a really rigorous survey. There are lots of different structures out there of different D values. But there are two big peaks. One is around about 1.3 to 1.5, and then there's another one at 1.7. And it's just due to the different types of processes. One is generated by turbulence, another's generated by cracking. So this 1.5 lies in that earlier kind of grouping of fractals. Yeah?
One more question. Sorry. One more question, and then we'll go to lunch, and then Richard will come back downstairs in Key West at 1 o'clock.
We see a lot of the same patterns in the large-scale structures of the universe, like the structures of galaxies and the galaxy filaments, and they seem very similar to smaller patterns, which are astronomically smaller
Yeah.
patterns here on Earth. Do you think that has its roots in physics and the fundamental forces?
I think it's not due to a shared physical process. I think nature generates these fractals for two reasons. One, how easy is it to generate it? And then two, are there any favorable characteristics that come out of it? So it's kind of, I started to get worried that there was this sort of giant conspiracy theory going on. There seemed to be all of these fractals everywhere. And you're right, the galaxy is fractal, and then some incredibly small things are fractal. But the shared thing is not the processes that are generating it, it's the favorable characteristics that come out of it. But all of this research has led to some pretty weird things. So the d-value of a galaxy is very similar to the d-value of the Pollock paintings as they evolved. And I get all of these emails from people saying, you know, they say, oh, I know how Jackson Pollock painted the fractals. He actually got kidnapped by aliens. And his paintings are the map of the galaxy showing where their home is. There's lots of amazing conspiracy theories about Pollock out there.
Let's thank Richard one more time.
All right, thank you.